Hello, we are continuing with blackbody radiation. In the previous video, we had discussed about the various attempts that were, or the formulas that were put forward by the likes of Wien as well as Rayleigh and Jeans, which somehow explained the variation, the energy distribution curve, which was something like this. The energy distribution curve for the black body radiation, and this was more or less the distribution. And we had a peak and a corresponding uh, wavelength to the maximum value of the energy of that peak. This was variation of the energy density with respect to the wavelength. And the attempts that were made, or the formulas that were given by Wien as well as Lord Rayleigh and James Jeans, well, for the first case in the Wien's formula, it was something like this, where it had a constant A divided by lambda raised to the power 5 e to the power minus b uh, divided by lambda times of kt, k being the Boltzmann constant, t being the absolute temperature. And was this was able to explain the higher frequency region. That means it was able to explain the this region where the frequency was higher, while it failed to explain the low frequency region, that was as the wavelength increased. Conversely, the Rayleigh-Jeans law, or the Rayleigh-Jeans formula, which was something like this, that is 8 pi nu cube divided by c cube k t d nu in the range of the in the range of the frequency nu to nu plus d nu. It failed to explain the higher frequency regions while successfully explaining the low frequency regions. So overall, there was no such formula which could explain this distribution that we had for the black body entirely. However, uh, in the year 1900, the famous person, or the famous scientist Max Planck, in his attempt, tried to explain the radiation, and he successfully did so, at least in the variation of that distribution curve. He successfully explained it by his empirical formula that he provided. Well, that empirical formula being simply u in the range in nu to nu plus d nu, that will be equal to some constant a times of nu cubed divided by e, that is the exponential term minus b nu divided by kt. Of course, he used the formulas that were provided earlier, but a little bit of modification into that, and he ended up with this empirical formula. And this was it. This was able to explain this variation, or this distribution of energy, quite successfully, as opposed to the previous attempts. Now, he made a bold hypothesis at that point of time, where he suggested that the energy is quantized, or the energy transfer is in the form of quanta. So the energy that is being transferred, energy transfer is in the form of packets, as quanta of energy, reducing it to a quantity. This was the famous hypothesis that he provided, which was of course proved by Sri S. N. Bose by the use of statistical mechanics. How exactly did he end up with this kind of a hypothesis? Uh, is that he considered the black body, the cavity walls of the black body, to be in thermal equilibrium due to the exchange of energy, and the exchange of energy between the various modes of radiation, and the atomic oscillators in the cavity wall were responsible for such things. Now he imagined that the atoms that were arranged, they were in the form of atomic oscillators. Now we can just have a spring model of small oscillations where the springs connecting the atoms, the arrangement of the atoms is such that they are vibrating about this their mean position, and as a result of that they were producing energy, or they had certain energy which was being exchanged between them. And this was the assumption that he made at that point of time. And the energy that he considered over here of an oscillator, that is the atomic oscillator, will be of a certain frequency. It will be oscillating with a certain frequency nu, and that nu will be restricted to certain integral multiple of the quantity proportional to that frequency. So this will be multiplied with some integral value only and no fractional value in between them. Thus the allowed energies were something like this. It was 0 or some integral multiple which was h times of nu, some value, and then it was 2h nu, and so on. So this was how the energy uh, was provided in the form of packets of h nu, and these h nu, 2 times of h nu and 3 times of h nu being the energy carried at one point of time, which is the quantity or the quanta that he had suggested, that I mentioned over here. Now the h is obviously, later on it was named as the Planck's constant, which bearing the value 6.62 times of 10 raised to the power minus 34 in joule seconds. And the oscillators cannot exchange energy with the radiation in an arbitrary continuous manner. So they have to exchange the energy in discrete amounts, leading to this quantized form. And thus, with these values, the average energy per oscillator can be calculated. Now, according to Planck's hypothesis, as the frequencies and the energies were of this order, we can have n number of oscillators to be oscillating within that cavity. So let n0, n1, n2, and so on be the number of the oscillators with the frequency nu, whose energies are n0s are the oscillators having the frequency 0 or the energy 0, the corresponding energy that is. And similarly with n1, the energy corresponding energy is h nu, that is one packet of energy or one quantity of energy. And then n2 are the number of oscillators which are having the energy 2 times of h nu, and so on. Now we wish to calculate the average energy per oscillator. So the total number of oscillators can be given as n, which is equal to n0 plus n1 plus n2, and they can go on with that. And the total energy that is possessed, or that is present for all the oscillators put together, we can give it as E, and that will be a 0 energy for n0 oscillators, and then h nu energy for n1 oscillators, right, and then h2h nu for n2 oscillators, and it continues like that. Now the oscillators are assumed to obey the Maxwellian distribution law, according to which the number of oscillators with energy, supposedly I denote it as something like a different energy, because I have already used this capital E notation over here. So let me use that somewhat epsilon type of notation there. So according to that Maxwellian distribution law, the number of oscillators with energy E, they will be proportional to the Boltzmann factor, which is given by E raised to the power minus of E by kT, where K is the Boltzmann constant and T is of course the absolute temperature. So we have the value of N1 in this case to be equal to some constant C multiplied with E minus h nu divided by kT, right? And for similarly for N2, we'll be having the value as C e to the power minus 2h nu divided by kT. Remember, h nu and 2h nu are for the values of the energy, which are corresponding to those number of oscillators. Now, as we add them up, what we get is n, which was equal to n0 plus n1. Well, n0 is simply Ce to the power 0 because the energy was corresponding energy was 0, and then plus C e raised to the power minus h nu by kT for n1, and then for n2 we had C e to the power minus 2 times of h nu divided by kT, and it continues. We just put this value, suppose we take the C as common, and what I have in brackets is 1 instead of e to the power 0 plus e to the power minus h nu by kT stays as such. Let me put that in bracket and have a power 1, and then C e to the power minus h nu by kT, and what I do is I take the power term, that is 2, the number outside, and so I have a form of 1 plus a squared and so on. The C is common, of course. So in that case, in case of a series like this where you have 1 plus a squared and the sum goes on, in this kind of a geometric series, the total sum results in 1 divided by 1 minus a, where a is obviously less than 1. So in this case what we get is C divided by 1 minus e to the power minus h nu divided by kT. That's all. Now remember, for the energy term what we had is E was equal to n0 times of 0 n1 times of h nu. Let me write that again for you. N0 times of 0 plus n1 times of h nu plus n2 times of 2h nu, the corresponding energies, and so on. Now we know the values of n1, n2 and everything of that sort, so what we get is the first one goes to 0 of course, because n0 times of 0 is 0, while for the second one we can take the h nu part to be common, and h nu goes common for all of them, so what we are left with is n1 plus 2 times of n2 plus 3 times of n3 and so on. Remember, n1 plus n2, and with all these values what we get is, if we substitute their original values that we had, that is for n1 we had C e to the power C e to the power minus h nu divided by kT, and I take the C will be common for all of them, so I take the C outside as well. So this is to the power 1 plus E minus h nu divided by kT to the power 2, but we also have a factor 2 over here, so we write that 2 over here as well. So now this If in this case what I do is I take the e to the power minus h nu divided by kt to be common, to be the common term, what do okay, I may not take that common, I can skip that actually, or should I? Okay, I take one of them as common, so I have 1 plus 2, 2 times of e to the power minus h nu divided by kt. I write an extra term for you to understand. This would have been raised to the power 3, but one of them is common over here. So this is e to the power minus h nu divided by kt whole squared, and it continues. Now this summation series is of the form 1 plus 2a plus 3a squared and so on. And the result for this summation is something like this: 1 minus a whole to the power 2. So 1 divided by 1 minus a raised to the power 2. So what we get in this case is c h nu e to the power minus h nu divided by kt whole divided by 1 minus e to the power minus h nu by kt squared. With this term and this term available, now we can calculate the average energy, which is somewhat represented like this. The average energy is going to be of the form E divided by N, that is the total energy of the oscillators divided by the total number of particles that are present. So means the total number of oscillators. So these total number of energy divided by the total number of oscillators, we have the values for all of them. Now the total energy that was obtained is over here, that is c h nu e to the power minus h nu by kt divided by 1 minus e to the power minus h nu by kt squared, and the denominator term will have the c at the bottom, and at the top it will be having 1 minus e to the power minus h nu by kt. Now this term cancels out with one of those terms and the c's get cancelled out. So what we have for the average energy is something like this, that is equal to h nu divided by, now this term that is left in that case, that can go down, and what we have is, instead of 1 we have e to the power plus h nu by kt, and this gets divided to the other term, which becomes 1. So now we have this as the value. So this is the expression for the average energy. Now the number of independent modes of frequency, independent modes of frequency, they range in the range, in the uh, frequency nu per unit volume. So this per unit volume is equal to the Jeans number, that was obtained, that we had provided, the Rayleigh-Jeans expression, that is 8 pi nu square divided by c cube. So this is the number of independent modes available. So the radiant energy will be, now the radiant energy that we have been discussing about, so that is u nu times of d nu, u as a function of frequency in the frequency range nu to nu plus d nu, is equal to the average energy multiplied with the number of independent modes per unit volume in the range nu to nu plus d nu. So we have the entire expression for the energy density in that range of frequency, that is 8 pi nu square divided by c cube, and we put the value of the frequency over there, that is value of the energy, average energy over there. So there's a nu over there and there's a h over there, so I keep those values. And this multiplies to e to the power h nu by kt minus 1 in the denominator, while the above terms are taken care of in the expression. So this is what the Planck's radiation formula is all about. Remember, in this previous page, I had provided with the empirical relation given by Max Planck, where we had a constant a at the top and a constant b at the bottom in the denominator in the exponential term. So from that, what we get is the value of a and b are something like this. This term that I've encircled right now, that is equal to the value of a. That is not entirely encircled because there was a nu square over there, I guess. Yes, there was a nu cube. So a nu cube. So we can keep the nu cube outside. We have the h within that. So a is simply equal to 8 pi h divided by c cube. This is the expression for the constant a, while for the constant b that was there, b is simply equal to h. If you observe that expression, empirical relation, where e to the power minus b nu by kt, so that b, instead of b we have the Planck's constant h over here. So these are constant values, as I had said earlier, which was obtained back then. And we have the variation, or we have the Planck's radiation formula within the given frequency range, that and it satisfies the whole range of frequencies, right from the very low frequency to the very high frequencies that were unsolved in the previous cases. Now, just to give you an idea about how it was able to explain those previous laws, if we have the formula over here, that is the entire formula, that I rewrite it again in the on a fresh page over here, that is u nu d nu equates to 8 pi h nu cube divided by c cube, and this is 1 by e to the power h nu divided by kt minus 1 d nu. At low frequencies, with frequencies tending to 0, that is, in those cases, if we observe this term, that is e to the power h nu by kt minus 1, well, the exponential term actually expands mathematically as 1 plus h nu by kt plus 1 by 2 factorial. This is the Taylor's series expansion, h nu by kt squared, and so on, minus 1, that is the one that was over here. So 1 and 1, they cancel out, and we neglect the higher terms because the value of nu there goes to 0. So with nu going to 0, the higher order terms can be neglected. So what we are left with is only this, that is h nu by kt. So if we replace that value over there in the denominator, instead of h nu, e to the power h nu by kt minus 1, we simply end up with h nu by kt, that is u nu d nu is equal to 8 pi, I rewrite it bit, h e nu d nu equal to 8 pi h nu cube divided by c cube, and in the denominator we have h nu by kt, so h nu stays there, kt goes up, and this is d nu, and one of the h can get cancelled out, and one of the nu gets cancelled out, so this is simply nu square. And if you can recollect a bit, this is nothing but the for lower frequencies, this is nothing but the Rayleigh-Jeans formula which we had discussed. Let me go back a few pages. If you There's the Rayleigh-Jeans formula, where 8 pi nu cube c cube kt, it's actually nu squared, not nu cube. My bad, uh, I've written it incorrectly over there. So this is 8 pi nu squared instead of nu cube. This one is not nu, this is squared instead of cube. So this is exactly what we are getting over here. Now at higher frequencies, for frequency tending to infinity, the term which is e to the power h nu by kt minus 1, as because this term becomes very huge in value when nu tends to infinity or goes to a very higher value, then the 1 can be neglected. So 1 being neglected, what we end up with is that we have u nu d nu equal to simply 8 pi h nu cube divided by c cube 1 by e to the power h nu divided by kt. The 1 is gone, and this is d nu, and this is exactly the formula that we had discussed. This was in lambda. If we are to take that in lambda, we'll have to use the case where we have nu is equal to c divided by lambda, and so we have d nu to be equal to minus c divided by lambda squared d lambda. And if we substitute that value over there, we have u lambda d lambda is equal to 8 pi h, and c divided by nu is simply lambda, so this is lambda squared, sorry, lambda cube in the denominator, and we have 8 pi h lambda cube, and here we have 1 divided by e h nu by kt, and well, that can be h lambda divided by c in that case. And instead of d nu, what we'll be having minus of c divided by lambda squared, and that minus sign can be taken care of because we had neglected that previously as well. So the minus sign is gone, and what we are concerned with is only the value, that is 8 pi h, and the c term over there at the top, divided by, this is lambda to the power 5, 1 divided by e h. Remember, nu is simply equal to c by lambda, so this is c divided by lambda kt or k lambda t, write it as you like, and this is d lambda over there. So this expression divided by lambda to the power 5 is exactly similar to this expression that we had obtained. And remember, the exponential term when taken to the top is having a negative sign in the power term, and the constant b is obviously hc, and at the denominator of that power term you have lambda kt, which is what I have mentioned over here right at the bottom. So we get both the laws that were explaining the higher and the lower frequencies pretty well from the single empirical relation, as well as proper explanation of quantization of the atomic oscillators present within the cavity of the black body radiation. So that is how we start with the quantum mechanical approach to various systems, and it was a pioneer in quantum mechanical explanation or quantum mechanical viewpoint to various things. It led to Bohr's quantization of the atomic orbit having the angular momentum quantized. It led to Einstein's explanation of the photoelectric explanation of the photoelectric effect, and many more things that followed. But this was the starting point, just the beginning of it. And the Planck's constant plays a vital role in all of those concepts uh, widely and properly. There will be more discussion on these kind of topics. We'll be starting off with quantum mechanics very shortly. Till then, thank you for watching.